Okay, Assalamualaikum and good morning.
Waalaikumsalam. Good morning, sir.
Okay, so today I would like to discuss about the harmonic distortion in the electric supply system. Okay, so actually this topic is under chapter 4 lah. Chapter 4. So last, if I'm not mistaken, last week I sent to you the chapter 4 notes, right? Chapter 4 notes about the harmonic. So this is one of the notes that I had given to you. Okay, so the topic is the harmonic distortion in the electric supply system. So basically, harmonic distortion. This is one of the power quality problem that happen in the electric supply system. Okay, so basically the harmonic distortion in the electric supply system. This is the try to do to see or to observe, to investigate what happened in the electric supply system when the level of a harmonic distortion is excess. If you refer to the IEEE regulation. So I hope you can see what is the level of the harmonic distortion, either voltage distortion or current distortion level in IEEE regulation, right? So basically from this technical note, so they discussed about the harmonic distortion. So this the technical note discuss about the harmonic distortion, its causes are, so the causes and the adverse effects, the impact of the harmonic distortion in electric supply system, right? About the causes here, the causes, and then the effect, and then what is the level unacceptable? Okay, what's level unacceptable? Okay, unacceptable. So the level unacceptable, we refer to the IEEE regulation that I had mentioned before, right? So I hope you can see what is the level of the voltage harmonic distortion and what is the level of current distortion. If we refer to the level of electric supply system and how to reduce it. Okay, and how to reduce it. Okay, how to reduce it means when the harmonic distortion assess the level under any regulation, and then how we reduce it. So we can use maybe the mitigation or solution to reduce the harmonic level. Okay, so integral energy, your local network operator or the integral energy power center can give you advice if you have particular concern with this issue. Okay, so that thing. Okay, so just so if you read here, they say we want to know the causes, so the effects, what the level of a harmonic distortion, and then how we solve it, right? How we solve it. So before that, so we have to know what is the harmonic distortion actually. So harmonic distortion is the change in the waveform of the supply voltage from the ideal sinusoidal waveform. Okay, so normally in the AC source, okay, AC source, normally we have the ideal sinusoidal waveform. But when harmonic distortion occurs, in the electric supply system. Okay, so our sinusoidal or our waveform is or non-sinusoidal waveform. Make it, I mean, a harmonic distortion will make the original supply waveform become or non-sinusoidal waveform. So this is the harmonic distortion. So basically, this harmonic distortion, it can caused by the interaction of distorting customer load with the impedance of the supply network. So it is a major adverse effects are the heating. Okay, so the effect is, so this is the effect. Apa kesan harmonik di dalam kita punya electric power supply? So its major effect here is what? The heating of the induction motor, transformer and capacitor, and overloading of neutral. Right. So this is the effect of the harmonic distortion. Means that when harmonic distortion level or percentage of harmonic distortion is excess the acceptable limit. Okay, acceptable limit means the effect is what you can see here, the heating of induction motor, transformer and capacitor. So means our induction motor, transformer and capacitor will experience with the high temperature. High temperature means, so harmonic will create the heating, the heat. Okay, the heat in the induction motor, transformer and capacitor. And then the effect is the overloading of neutral. Okay, overloading of neutral. Okay, so overloading of neutral means, back to the basic concept of electric power supply. So we have a three-phase system. Three-phase system. Okay, so from a three-phase system, you have red, yellow, blue, neutral, and ground. Right? Red, yellow, blue, neutral, and ground. So the main part here is the red, yellow, blue as a live phase, and then the other one, the more important is a neutral line or neutral cable. So due to the harmonic level is excess the acceptable limit, means your neutral current, okay, your neutral current will be created in electric power, supply, power supply. Okay, electric power supply means instead of your neutral current is equal to 0 for balance system, due to the harmonic level, so it can make your neutral current is not equal to 0. So this is the effect of the harmonic distortion. When your neutral current is not equal to 0, so means your system in unbalanced system. Okay, so that is the reason why harmonic distortion. So we sorry, harmonic distortion level is more important in electric power supply. So how they reduce it? So power factor correction, capacitor can amplify harmonic to unacceptable value in the presence of harmonic distortion. So standard specified the major harmonic voltage which can occur on the network, 5% total harmonic distortion being critical. Okay, so a number of harmonic mitigation techniques are listed to be used where the limit in the standard are exceeded. Okay, so from this technical note, if you read here, so automatic you can understand why harmonic, what is the harmonic distortion, what is the effect, and then the other one is the what we call the level of the harmonic distortion, and then what is the technique that can be used to solve the harmonic distortion level problem. Okay, do you understand? Hello? Hello?
Yes, sir.
Okay kah?
Yes, sir.
Okay. Actually kalau you all baca, actually you all akan nampak sikit kalau you all baca lah. And then you all take note the important point in this technical note and or any notes that I have given to you. So actually you understand what is the harmonic dispersion all about. Itu maksud saya sekarang ni. Kat sini tu kalau kita baca kat sini you akan nampak dia punya the important point yang berkait dengan kita punya harmonic distortion tu sebenarnya. So harmonic distortion ni secara ringkas je, very simple punya understanding untuk harmonic distortion. Harmonic distortion ni memang berlaku di mana-mana power supply, sama ada 3-phase system ataupun dalam kita punya 3-phase system lah. Jadi dalam 3-phase system kita pada 3-phase system, so kita akan nampak the effect of the harmonic distortion. Right. Okay, so now we go to the next slide. Okay. Okay, so the content. Okay, I think there's nothing. Okay, the ideal supply. Right, the ideal supply here. Okay. Okay, so the ideal low voltage single phase supply is to follow both RMS, okay, RMS lah, at a frequency of 50 Hz and with a sinusoidal wave shape as shown in figure 1. Okay. So if you refer to figure 1 here, this is the ideal sine wave. So what we can see here, for the ideal sine wave, so the frequency, this ideal sine wave consists of only one frequency, fundamental frequency, which is 50 Hz. Okay, so kat sini kita nampak just single waveform. So they contain of only fundamental frequency 50 Hz. And with a sinusoidal wave shape as shown in figure 1. Okay, so from the figure 1 here lah. Okay, so until the 1960s, most customer loads through a current waveform which was also sinusoidal. Okay, sehingga 1960 kebanyakan load dia akan bawa current dalam keadaan sinusoidal lagi. Okay, so such loads include induction motor, incandescent light, stove, and most household appliances. So the power system has impedance which restricts the flow of current, mainly due to the magnetic flux effect in substation, transformer, and transmission line. Okay, nothing you want. So the impedance is unavoidable and leads to a voltage difference between the supply, substation, and customer load. Reduction of this impedance is generally impractical and expensive. Generally, the customer voltage is less than at the substation. So nothing on that. That just explain about the impedance of what we call the power system. Okay, that one. Okay, so and then now, so from the ideal supply, which is consists of a single frequency 50 Hz. Okay, 50 Hz. And then how the harmonic distortion is growth in the power supply. So the growth in harmonic distortion is inevitable. So the actual power system voltage can depart from the ideal sine wave in several respects. Harmonic distortion is the name for a departure in which every cycle of the waveform is distorted equally. What is mean the distorted equally? So distorted equally mean so for each for every cycle, okay, for every cycle here. So every cycle of the waveform. So like if we refer to the figure C here, okay, for each cycle, so we can see the harmonic contents in the positive cycle and negative cycle, positive cycle and negative cycle here. So figure 2A, or figure 2A shows a distortion which appear on one cycle, okay, on one cycle due to the switching of power factor correction capacitor on the power system. Okay, so this is caused by power factor correction capacitor on the system. This is not harmonic distortion. So this is more to switching. So switching means that this is the transient. If you refer back to chapter 3, we discussed about the voltage swell. So one of the causes is the switching of the capacitor in a power system. So you can refer back to chapter 3, right? So this is not a harmonic distortion from figure A. However, the distortion shown in figure 2B and C a form of harmonic distortion, giving flat top and notching effects respectively. So flat top here, so you can see what is the flat top. Okay, so flat top here you can see at the highest value of this sine wave here. So the one is a flat top here. So flat top is a flat top, and then the other one is from figure C, notching effect here. So for each single cycle here, you can see the notching effect in the waveform. So type of distortion, non-harmonic distortion. So B is the flat top harmonic distortion, and C is a notching harmonic distortion. So from the waveform, so actually we can identify which is whether your power system, your electric power system having harmonic distortion or not. Okay, from the waveform. So we can observe through the waveform, right? So harmonic distortion is not generally due to the operation of the power system. Okay, so you just take note this one. Harmonic distortion is not generally due, kan disebabkan oleh power system operation, and was largely absent before the 1960s. And about this time, a different type of customer load with electronic power supply become popular. So this so-called distorting loads draw a non-sinusoidal current as shown in figure 3A and 3B. So the first type is drawn by electronic office. Okay, so you can see figure 3A and figure 3B here. Okay, figure 3A and figure 3B here. So that is the current waveform drawn by that one is A, personal computer, and B is a DC variable speed drive. So here the first type is drawn by electronic office equipment such as computer and fax machine and household appliances with electronic control, such as the more sophisticated type of washing machine. So the second type is drawn by variable speed motor drive, such as used in factory, manufacturing line, and lift. Okay, So now here this paper explain this type of waveform here. So wait, okay, so this type of waveform can be shown to be made up of a combination of sine wave. Okay, so masuk sekarang ni, kalau tak ada harmonic distortion, mean you ada just a single frequency ataupun fundamental frequency original lah, from the original sine wave, you just ada 50 Hz for the nominal fundamental frequency. Tapi sekiranya berlakunya harmonic distortion, so di dalam waveform yang kita ada sekarang ni, dia kata apa? So this type of waveform can be shown to be made up of a combination of sine wave. One of the supply frequency, one at the supply frequency, and the others are higher frequency. So waveform A contains sine wave. What you refer to? Which figure? Figure 3A. Okay. Waveform A contains sine wave at frequency 50, 150, 250 extra, while waveform B contains frequency 50, 250, 350 Hz extra. The magnitude and the frequency of the high frequency component is a characteristic of the type of distorting load and can enable it to be identified. So the distorting component flow through the power system and give additional high frequency voltage drop, which modify the voltage waveform at all nearby customers. So in the case shown in figure 4, there will, from a figure 4, there will be no distortion at bus 1. Bus 1, more at bus 2, and a large distortion at bus 3 because of the increasing system impedance further from the supply point. So current waveform figure 3A and B give flat, figure 3A and B give flat top and notching type voltage distortion respectively. Figure 3, flat top and notching. Okay, masuk dia sekarang ni kat mana sebenarnya ni? Okay, kalau kita baca sini, refer figure 4, how distorting loads affect nearby installation. Okay. So in the case shown in figure 4, there will no distortion at bus 1. Means that harmonic distortion level in terms of percentage lah, harmonic level at bus 1 is lower than at bus 2, and then the harmonic level at bus 2 is lower than harmonic level at bus 3. So normally at the bus 3 here, So this is the higher harmonic distortion because of loss to the distorting current. So distorting current actually created, okay, maksud sekarang ni kita punya distorting current ni, current yang distorted lah, current yang distorted yang disebabkan oleh load. So bila load yang kita gunakan tu, apabila power supply kita sambung ke distorted punya load, distorted current ni that can reflect back to our bus 3, bus 2 and bus 1. So what we can see here from the distorted load, so the distorted current that can effect kepada harmonic level bus 3, bus 2 and bus 1. So the highest harmonic level yang what we can see at the bus 3. So actually harmonic distortion sama ada voltage distortion ataupun current distortion are created, dia tercipta after we connect the power supply to the load. Selepas kita sambung power supply kepada kita punya load, barulah dia punya current atau waveform, current ataupun voltage distorted. Sekiranya kita tak sambung power supply ke sistem, power supply ke load, maksud saya load yang tidak memberi, yang bukan sensitif punya load lah. Ada yang sensitif, ada yang non-sensitif. Kalau we refer back to type of load, type of load kita ada dua, linear and non-linear kan. So biasanya yang non-linear ni lah, non-linear yang akan create harmonic distortion sama ada voltage ataupun current. So linear load dia tak create harmonic distortion ataupun current distortion. Tapi non-linear load yang akan create harmonic distortion and current distortion, linear and non-linear. Okay, so from this paragraph, so they explain the harmonic level at different bus, close to the distorted load and then far from the distorted load, right, from figure 4. The supply frequency component, 50 Hz, like in Malaysia lah, is called the fundamental. So as I mentioned before, so the higher frequency component, okay, so the higher frequency component, this is the multiple frequency. The higher frequency component will always be an exact multiple of the supply frequency. Multiple of the supply frequency, and then we call as harmonic. Ni harmonic lah. Okay. So the ratio of the harmonic frequency to the supply frequency is called the harmonic order. So harmonic order ni dia punya ratio of the harmonic frequency lah. So for example, from figure 3A contains the odd harmonic order. Dia ada harmonic, dia ada odd ataupun even, genap ataupun ganjil. Okay. Odd harmonic order 3, 5, 7, 9, 11 and so on. While waveform figure 3B contains the odd harmonic which are not multiple of 3. Example 5, 7, 11 and so on. So depend on the type of what we call the distorted waveform. So from distorted waveform, so actually we can see through the bar graph lah, harmonic graph. That waveform contain of what? maybe just 357 or 5711 and so on. So from there we can see the harmonic order in the distorted waveform. Okay, so that one is the harmonic order. So it can be seen that harmonic distortion is a phenomena in which customer affect each other through the common connection with the electric power system. It has been discussed earlier that the presence of a system is unavoidable, so that the growth of customer load. Okay, so this term actually. Okay, this important. So thus the growth of customer load with electronic power supply has meant that a growth in the harmonic dispersion of power system is inevitable. So as excessive harmonic distortion degrades some type of equipment, so it is important to be able to calculate harmonic levels and reduce them in some cases. So sekarang ni day by day, year by year, so normally the type of load, okay, the type of load in the world become more sensitive, more sophisticated, and then so actually you can see so a lot of electronic device consists of our power supply from AC to DC, from DC to DC, and then we back to the power electronic issue lah. Okay, power electronic issue. So that is the reason why from time to time, from year to year, so the harmonic distortion issue is very important to be discussed and then to be solved or to be reduced the harmonic level in power system. So that is the main important here. Okay. So you can see here is more important. Why harmonic level in power system important ataupun kita kata sebagai salah satu isu yang penting di zaman sekarang lah. So how harmonic distortion can affect your equipment? Macam mana dia boleh affect kita punya equipment kat sini? Kalau kat sini kalau kita baca, kalau kat sini kita lagi baca sini dia kata apa? Kita baca di sini. Ni isu dia lah. Ni isu yang penting. So how harmonic distortion can affect your equipment? Macam mana harmonic level ni boleh memberi kesan kepada kita punya equipment ataupun alat-alat kita sebenarnya. So equipment responds to harmonic differently depending on their method of operation. So of course. So for example, okay, just one basic example here. For example, incandescent light and most type of household electric heaters and stove are not affected adversely at all. Okay, so kat sini tak berlaku punya orang kata apa? Effect kat sini. But on the other hand, apa yang berlaku sekarang ni apabila harmonic level tinggi, induction motor winding are overheated by harmonic. Overheated lah. Overheated by harmonic, causing accelerated degradation of insulation and loss of life. So harmonic voltage can give correspondingly higher current than do 50 Hz voltage, and one can easily underestimate the degree of additional heating in the motor. So higher current. Okay. So the operation of some equipment depends on an accurate voltage wave shape, and they can malfunction. Okay, the first one is heating, and then the second one is malfunction when harmonic present. So example of this equipment containing SCR, silicon control rectifier, okay, or we call as thyristor. So the one this is the device that we use in the power electronic switching, such as light dimmer and shift builder. Harmonic due to many single phase distorting loads spread across three phases. Okay, harmonic due to many single phase distorting loads spread across three phases, such as occurs in commercial office building, can give neutral current exceeding the active line current. So as mentioned before, so when harmonics are absent, the neutral current carry a very small current. Okay, kalau harmonic tak ada, neutral conductor carry a very small current, and it has been the practice to rate the neutral for all of, or maybe for half of the active line current. But with excessive level of harmonic due to single phase load, there is the risk of overloading the neutral with two possible consequences. Okay, one is overheating the neutral conductor with loss of conductor life and possible risk of fire. And then the second one, they have been claimed that the high neutral voltage can affect digital equipment and local area network LANs if the earthing system is poor. So this is what happened in neutral conductor. Apabila harmonik tinggi, ni yang dikatakan overloading of neutral. Dan ada dua possible keadaan yang boleh berlaku kepada neutral conductor. Yang pertama, overheating in neutral conductor, and then the second one is the high neutral earth voltage. So dua benda ni yang penting lah. Dua benda ni yang penting. Right. So in the supply system, substation, transformer and power factor correction capacitor are most affected. Kita punya substation transformer lah. Transformer are affected by a distorted current waveform which can cause extra heating, leading to a reduction in their service life. That means jangka hayat transformer kita lah. That means harmonic level bila tinggi, bila lama-lama kita punya transformer, kita punya even neutral conductor yang tadi, kan, kita punya jangka hayat, sepatutnya kita boleh boleh guna transformer tu dalam katakan 10 tahun dia katakan maksimum. Tapi sekarang ni bila harmonic level kita tak kontrol, so maksud dia punya jangka hayat tu dia berkurang, mungkin jadi 5 tahun, 6 tahun. So kita kat situ kita nampak dia punya keburukan lah, dia punya disadvantage of the harmonic distortion lah. So capacitors are affected by the applied voltage waveform which can cause overheating of the dielectric with a risk of explosion. So boleh menutup lah kapasitor kalau harmonic tinggi. So many plant engineer are aware only of system problem which lead to immediate malfunctioning or equipment failure. So we have seen the harmonic effect can lead to equipment overheating and reduction the service life by the factor of up to half with consequent economic loss. So unlike most other type of supply problem, harmonic can go unnoticed for many years unless equipment temperature or the voltage waveform is routinely monitored. Okay, maksud sekarang ni kalau kita boleh monitor kita punya the level of Maksudnya kalau kita nak increase dia punya service life ataupun jangka hayat equipment kita, maksudnya kita kena buat monitoring lah, rutin punya monitoring untuk tahu level harmonic yang ada di dalam power system, electric power system kita. So that is the issue lah. So task yang ni memang kita bagi kepada plant engineer lah. Okay, yang mana yang plant engineer kat sini biasanya kita panggil sebagai chargeman lah. Chargeman pun dia ada level-level chargeman yang boleh masuk substation, level chargeman biasanya kita tengok voltage level punya kelayakan lah. Kadang-kadang dia boleh pergi kepada 33k, dia boleh masuk 11k, 11 kV, ataupun dia boleh pergi tengok 33 kV, tu chargeman yang biasa yang ada kat Malaysia lah, dia punya level. Okay, so tu task yang I mean person in charge lah, person in charge untuk routinely monitored. Okay, routinly monitored. Then this one is capacitor. Resonance can magnify harmonic problem. Okay, so wait lah. Okay, power factor correction in the presence of harmonic. And then the measure of harmonic distortion, harmonic standards, harmonic analysis, harmonic analysis. Okay, so kalau kita refer balik kepada yang tadi, as I mentioned, dia kata routinely monitored. Maksud sekarang ni untuk kita control kita punya harmonic distortion level, sama ada voltage ataupun current. So kita kena ada buat monitoring punya schedule lah, kena check dari situ. So untuk harmonic bila kita nak once bila kita dah buat what we call monitoring tadi tu, kita perlu dah tengok ataupun kita perlu analyze kita punya harmonic. Okay, so here there are some simple methods for estimating the harmonic voltage due to an insulation and whether a capacitor may cause an unwanted dissonance. The steps in a simple harmonic analysis are, okay, from the data monitoring, data that you monitored from the at your electric power supply punya plant ataupun substation, for example. So the step here, this is the step in a simple harmonic analysis are, okay, yang ni dia kata apa? So obtain information on the supply system. Okay, that means you have done the monitoring schedule, so you can obtain the information on the supply system. This is usually given in the form of the short circuit current or fault level, so from which an equivalent impedance can be calculated. So estimate the major harmonic sources in an installation. Some guidance from this is given in reference 3 or sini. So for each harmonic level, for each harmonic order, model the power system and installation. It is assumed that inductive reactance will increase with frequency. Capacitive reactance will decrease while resistance remain unchanged. So determine the voltage at the point of common coupling PCC from the distorted current injected and the calculated harmonic impedance. So this is the how we can do the harmonic analysis daripada data monitoring yang kita buat. Okay, kat situ. And then kat sini kita ada apa? Kat sini kita ada harmonic standard kan. Harmonic standard. harmonic standard. And the measure of harmonic distortion. Customers should be interested into aspect of harmony, equipment susceptibility and equipment emission. So the first is the degree of distortion, which will cause equipment damage or malfunction and is characterized by the harmonic voltage which the equipment can tolerate. So the second is the measure of how equipment will affect the supply and is characterized by the harmonic current tone. So consider the case of voltage waveform distortion. Although similar idea is applied to current, there are several measures of the harmonic distortion, including the level of the voltage at each harmonic. Two in particular are total harmonic distortion, so this one, and not that. So the first is important for long-term thermal effect. The second for equipment malfunction. Okay, so for the long-term thermal effect, this one is total harmonic distortion, THD, and then for the equipment malfunction, we refer to the not that. Okay, not that. Okay, let voltage waveform have R and F value V, and the fundamental and harmonic component V1 and Vh. Let a voltage waveform have R and value V, and the fundamental and harmonic component V1 is the fundamental and Vh the harmonic component. So these three values are related by the equation. So V square equal to V1 square plus Vh square. So for example, if harmonic voltage of 10 volt is added to a sine wave of 240 volt, the RMS value of the two together is 240 volt for fundamental lah. So V square 240 square plus 10 is the harmonic given 240.2. So THD is measured by the ratio of harmonic voltage to the fundamental expressed as percentage. So THD harmonic 10 over fundamental. So for example, in the above case, our total harmonic distortion is 4.2%. So this is a simple calculation for the how we calculate the harmonic distortion. Okay, so here power factor correction. Capacitor resonance can magnify a harmonic problem. Macam mana dia kata ni? So kat sini dia kata apa? Okay, so the size of a capacitor is really given in terms of the power generated QC. Let the fault level at the point of capacitor correction be FL. If both are measured in consistent unit, example MVR, MVA, then resonance will occur at harmonic order and resonance. So there is a rate of harmonic resonance in this number is close to the harmonic order present in one of the harmonic load. For example, okay, they've given the example here. So for example, suppose the fault level is 100 MVA and a capacitor bank had rating 800 kVR, given the NS is equal to 100 divided by 0 equal to 11.2. So this is close to the harmonic of order 11 produced by many types of harmonic loads, and there is a strong risk of resonance with any nearby distorted load of this type. So if the capacitor bank could be reduced to 500 kVR and resonance increase to 14.1, okay, 14.1, and the risk of resonance is less. So this is how we calculate the resonance, the resonance here. Power factor correction. Power factor correction in the presence of harmonic in the voltage N or current waveform is a confusing object. We begin with a brief discussion of the rationality of PVC when harmonic are absent. The total installation current has two components of current at the supply frequency. A power component, which is in phase with the voltage, and another so-called reactive component. The relationship between the total current and these two components is I total square is equal to I power square plus I reactive square. So mean I total is square root square root lah. Square root 1 square root. So sekarang ni daripada equation 2, the power factor of N installation is given by power factor I power divided by I total. So as an example, a 20 kilowatt motor will typically draw 1 I equal to 19 ampere, and I reactive current is 14 ampere. Using equation 2, and then we can get the I total equal to 32 ampere, and equation 3 give power factor 0.9. So the NSW service and installation rule March 1939 required customer to maintain their power factor between 0.9 lagging and unity, but in Malaysia 0.885. Okay, some utilities have a tariff structure which encourage a customer to keep their power factor as close to unity as possible by reducing the reactive current. So means that if you want your power factor close to unity, so you must reduce the reactive current. So this can be conveniently done in most instances by the provision of suitable size shunt capacitor. So we can control the reactive current by control the shunt size of shunt capacitor. When harmonic are present, the current has an additional high frequency. So high harmonic distortion means high. You have a lot. We have more high frequency in the waveform component, and equation 2 has to be modified to sekiranya berlakunya harmonic. Okay, current dia akan ada additional high frequency. So kita akan add another term in the I total, means I power square plus I reactive square plus I harmonic square. Okay, bila adanya high frequency. In many cases, for example, with computer installation, I reactive is close to 0. So this for the case computer installation, but I harmonic is large and the power factor is less than 1. So if such a customer install power factor correction capacitor, then I reactive increase due to the capacitor current, further increase I total, worsening the power factor. So this is also the additional problem that harmonic resonance may occur, as discussed previously. Oh, so masuk sekarang ni sebab apa? Masuk sekarang ni sekiranya dalam sistem kita ada harmoni. Okey, dalam sistem kita ada harmoni. Dalam this paragraph lah dia cakap, dalam sistem kita ada harmoni. So biasanya reactive current is close to 0 lah untuk computer installation. Tetapi apa yang berlaku adalah harmonic current ataupun I harmonic. Harmonic current memang tinggi dan menyebabkan power factor kurang daripada 1. So ada customer yang install power factor correction capacitor. Okay, bila kita install power factor correction capacitor, apa yang berlaku adalah I reaktif akan increase. Reactive current akan increase disebabkan oleh capacitor current. So that's why dia cakap sini, then I reactive increase due to the capacitor current further increasing I total. Dia akan menyebabkan I total akan jadi increase, akan menyebabkan kita punya power factor jadi lagi lebih teruk lah. Lebih lagi ini bukan dalam spek yang kita nak lah. Kalau kita spek kita nak dalam 0.85 hingga 1 katakan, mungkin dia akan menyebabkan berlakunya lagi dekat rendah daripada 0.85, mungkin 0.7, 0.6. So this is also the additional problem that harmonic distortion may occur as I discussed previously. So sekarang ni, isu dia sekarang ni, yang saya cakap kat sini, power factor correction is the present of harmonic. Okay. Yang ni dia kata, yang saya faham kat sini, apabila kita install kita punya power factor correction capacitor, boleh menyebabkan berlakunya orang kata apa? Kita nak reduce reactive current tu ya. Kita cuba nak reducekan reactive current. Kita cuba nak reducekan reactive current, tapi apabila kita install power factor correction capacitor, dia akan menyebabkan I reactive akan increase. Reactive current akan increase due to the capacitor current, further increasing total current, akan worsening the power factor. So yang ni kita kena check lah dia punya isu dia kat sini. Harmonic standard. Yang ni harmonic standard. Customer need to be protected from other consumer producing excessive consumption on supply and imaging equipment or causing inconvenient malfunction. So Australia, okay, dia Australia lah. Australia has a several standard which address this problem. So the standard address three aspects of harmonic. The maximum level of harmonic voltage which are allowed on the supply. The maximum distorting current that household appliances can draw to ensure that the level in one meet. So the maximum distorting current and industrial installation can draw to ensure that the level in one meet. Okay, dia orang di Australia dia orang letakkan ada maximum level of harmonic voltage. Maximum level of harmonic voltage depend on dia punya voltage level lah. Voltage level. Di distribution level, transmission level ataupun generation punya level. So biasanya sekarang ni dekat transmission level ataupun distribution level lah. Okay, so untuk control dia punya maximum level harmonic voltage kat sini, dia bagusnya dia orang ni, dia orang dah letak the maximum distorting current that household appliances can draw to ensure that the level in one and meet. Dia orang letak kat situ. Dekat gantung kepada kita punya alat-alat rumah kita. household appliances. So the maximum distorting current that industrial installation, sama ada di rumah ataupun industri tu, dia boleh letakkan dia punya label, the maximum distorting current kat sini. I mean maksud dia pihak sama ada di rumah, household lah, sebab ada household appliances kat sini. I mean di peringkat domestik lah, dia orang control dia punya equipment dia orang. Okay. Berapa dia punya maximum distorting current yang dibenarkan. Dan di industrial punya level, dia orang pun letakkan dia punya berapa maximum distorting current yang dibenarkan. So the present limits on harmonic level in 415 volt supply system is 5% THD, 4% on odd harmonic, and 2% on even harmonic. So you can refer to reference number 2 lah. So a new Asron standard is due to be released date. Okay, this one again. Okay, so this limit apply at the point of common coupling PCC. Kat mana PCC? Ni PCC ya. The nearest point of connection for other consumer. Jadi dekat item substation. Okay, PCC defined as the nearest point in the power system to which another installation might be connected. Maksud sekarang ni kat sini, point ni lah yang kita gunakan untuk sambungkan kepada consumer yang lain. Contoh kat sini katakan satu consumer, dekat point ni juga kita akan sambung kepada another consumer. That one is the nearest point of connection for other consumer di sini. So this limit apply at the point of common coupling. PC defined as the nearest point in the power system to which another installation might be connected. Okay, so the standard is expected to be replaced later this year with some effect of limit given. Yang ni dia kata okay, tak penting lah ni. Saya tu lah. Tapi sekarang ni yang penting kita punya ni. Okay, yang ni yang kita perlu faham lah. So saya harap you boleh baca tengok dalam IEEE atau Malaysian punya dekat Malaysia apa standard yang Malaysia pakai untuk harmonic standard ni, and then apa label-label yang dia orang pakai, apa yang label berapa dia punya maximum level harmonic yang kita guna pakai. Okay, saya harap you boleh dapatkan harmonic standard, Malaysian harmonic standard lah. Kalau sini kalau kita boleh cari dia punya harmonic. Ya. Managing power system. Managing power system. Ya. Tak ada. Tak ada. So far tak apa. So hello. Are you there?
Yes, sir.
Okay.
Yes, sir.
Minta senario cari dapatkan info tentang harmonic standard yang ada yang Malaysia pakai boleh? Ni. So lebih kurang yang ni sebenarnya ni. Saya tak jumpa pula. Tak mahu buat. Okay. So hari ni kita tengok yang ni je lah. So ada apa-apa nak tanya? Ada apa-apa nak tanya? Tentang harmonik ni.
Ada, sir.
Tak ada.
Ada, sir.
Yang lain?
Saya pun tiada, sir.
Oh, tak ada ke? Pandai-pandai kamu semua ni. Aduh. So nota ni saya dah bagi kat kamu, minta you edit, you boleh baca balik lah nota ni. Yang explain nanti video saya bagi balik kat you all. So kalau tak ada apa-apa, thank you very much for joining my class. Hello.
Yes, sir.
Thank you, sir.
Sir.
Thank you. Thank you, sir.
Thank you, sir.
Thank you, sir.